All right, here we go for part two. Boring old, just take the derivative. No problem. Take the derivative of the left side, and that's just y prime. On the right side, I could think of this. This looks like a chain rule problem, right? So the derivative of the mother is the mother is ln x, so it's 1 over whatever, right? The 1 over the baby stays inside. But then I got to take the derivative of the baby, which is just 2x. And then now simplify that. 2x over x squared. One of the x's will cancel out, so I'm left with 2 over x. Some people might have thought, well, you know what? Can't we just use a log rule and put the 2 out in front? Yeah, sometimes it helps to simplify functions first before we take the derivative, and this is one of the cases. In fact, if I take the derivative here, the 2 is just hanging out front. The derivative of ln x is 1 over x, and yeah, that was a little bit easier. It wasn't that hard in the first place, but here we go. So this one is a chain rule question for sure. We have to write this one in a different form first, I'd say. So we've got log base 3 of x to the exponent a half. The first step is to think of this as a chain rule. This thing to the exponent a half, the derivative, the half comes down in front, baby stays inside, subtract that, 1/2. And then now I've got to take the derivative of the inside, derivative of the baby. Derivative of log base 3 of x is 1 over x. Not just 1 over x, though, because since it's base 3, I got to do the ln of 3. And tidy this up a little bit. Yeah, probably we should, I suppose. Negative square root, that goes on the bottom then. The 2 is on the bottom. Notice this x I'm going to put with this. I suppose, if I wanted to, I could put all the number parts together. And the number part here, ln 3, is just a number. And then the x, this is kind of like the number part. This part is the square root of log base 3 at x. A bit of a mess, this derivative, but that's what it is. BC. Oh boy, look at this huge chain rule problem. So we got ln of big thing. Well, the derivative of a log is 1 over big thing. 1 over big thing, x minus, it looks terrible. This looks terrible. But when I'm dividing by something, I just flip and multiply. So this is actually just going to flip up to the top. But now I got to take the derivative of the inside. The derivative of the inside thing, the derivative of the square here, of the baby, is a quotient rule, right? So derivative of the top right down the bottom, subtract the derivative right down the top. Derivative of the bottom is just 1 over the bottom squared. Okay, now I got to tidy this up, get you out of the way. This flips up to the top here. What was that? That was a 3 on the bottom. Good, nice handwriting there, Estelle. So x plus 3 over x minus 2 on the bottom. And then I'm going to tidy up the top here. I've got x minus x, that's gone. 3 minus negative 2 is 5 over x plus 3 all squared. But notice that since I've got factors here, there's no pluses. I can cancel out an entire bracket there, and then I am left with the derivative 5 over, and then there was an x minus 2 from here and an x plus 3 from there. And there's the derivative. Now, so, well, hang on, Restall. I remember from log rules that when I divide something on the inside, it becomes subtract on the outside. Could I use that to change the form of the function before I take the derivative? And yes, aren't you clever? You should have done that because it's way easier. Have a look at this. So if I have the ln of this quotient, when it's dividing on the inside, it's subtracting on the outside, then these are easy derivatives to take. The derivative of this piece is just 1 over x minus 2. The derivative of this piece is just 1 over x plus 3. And then I can do a little bit of tidying it up and I get the same thing. Notice that I would be okay leaving it like this, I suppose, right? Maybe this is easier to set equal to 0 and solve, but this was an easier derivative to take, wasn't it? If I was smart enough to realize that I could use a log rule. All right, D. D looks like an exponential function times a log function. This is a product rule. So mix a little Leibniz notation in there. Derivative of the first thing is just that thing times the fudge factor, ln 2. And then write down the second thing, plus, because it's a product rule, write down the first thing, derivative of the second thing. The derivative of the second thing is 1 over x, but remember 1 over x, and then the fudge factor. The fudge factor, so it's not quite the natural log. Can I tidy this up? A little bit. I see a common factor there. Maybe I'll write that out front. Doesn't tidy that much more than this, though. Ln 2 log base 2 at x plus 1 over x ln 2. I suppose I could try and get a common denominator there, but I think it'll be a mess. Probably this about as good as you'll need to do. And in fact, in this case, because that common factor never cleaned things up very much, probably you'd be okay stopping there. All right, what's next? Find the equation of the tangent to blah, blah, blah at x equals 1. Okay, typical problem, calculus problem, find the equation of a tangent. Just trying to look for my notes here, make sure I don't goof up any derivatives. Okay, so equation of the tangent, we know we need to get the slope, so we're going to take the derivative. Are we going to change the form of this? Yeah, let's use a log rule and change this just so it's a little bit tidier. I think it's still a quotient rule, though, right? Still a quotient rule because I got an x on the top and an x on the bottom. Still a quotient rule. So let's take the derivative. I'm going to think about the derivative over here just so I have more room to work later. Derivative of the top is 2, 1 over x, right? That's the derivative of the top. Write down the bottom. Minus, write down the top. Derivative of the bottom is just 3 over the bottom squared. Okay, now let's tidy. Notice there's an x there and an x there in that term. This is just going to be 6. Does this tie? Well, there's a 6 there as well. So let's 6 minus 6 ln x over 9x squared. It looks like if I wanted to, I could cancel a 3 right there. See that? I could cancel a 3 if I wanted to. Divide everything by 3 and I get 2 minus 2 ln x over 3x squared, I believe. And is this, is it going to get better than this? Well, not really, but we don't really care because we're going to substitute x equals 1 in here, right? We want this when x equals 1. So y prime when x equals 1 is 2 minus 2 times the ln of 1, which is 0, over 3 times 1 squared is easy to do in my head. So that's going to be 2 over 3. That's what the slope is 2 over 3. Fine. I could have substituted it in back there. So therefore, my slope is 2/3. Let's get my equation going here. Equation of the tangent, where the slope is 2/3. My x value is 1. What's my y value? My x value is 1. What's my y value? Well, I got to substitute back in here. So my y value is the ln, or 2 times the ln of 1 over 3 times 1. Well, that's 0, isn't it? That's 0 because the ln of 1 is 0. So y1 is 0. 2/3 x minus 1. I'm going to multiply by 3 to kill the fraction there. expand, and then I'm going to put this in standard form this time, just for funsies. And that's it. That's the required equation. Do I got another example? Feels like I got another example left in me. How are we doing for time? Should I? Yeah, I'm going to stop and do the dreaded part 3.